StatQuest is growing up. StatQuest is growing down. StatQuest is growing. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about decision trees. Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, doesn't have to be the same on the right side. On the right side, the question about donuts is asked first. Lastly, the final classifications can be repeated. For the most part, decision trees are pretty intuitive to work with. You start at the top and work your way down and down till you get to a point where you can't go any further, and that's how you classify a sample. Oh no! Jargon alert! The very top of the tree is called the root node, or just the root. These are called internal nodes, or just nodes. Internal nodes have arrows pointing to them, and they have arrows pointing away from them. Lastly, these are called leaf nodes, or just leaves. Leaf nodes have arrows pointing to them, but there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node. And most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease, they are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Gini. To be honest, I don't know why it's called Gini. I looked around on the internet and couldn't find anything. However, if you know, please put it in the comments below. I would love to know. Regardless, the good news is calculating Gini impurity is easy. Let's start by calculating Gini impurity for chest pain. For this leaf, the Gini impurity equals 1 minus the probability of yes squared minus the probability of no squared. Now let's plug in some numbers. The probability of yes equals 105 divided by the total number of people in this leaf node. And the probability of no equals 39 divided by the total number of people in this leaf node. After we've done the math, we get 0.395. That is to say, the Gini impurity for the leaf node on the left equals 0.395. Now let's calculate the Gini impurity for this leaf node, the one on the right. Just like before, it equals 1 minus the probability of yes squared minus the probability of no squared. And the probability of yes is 34 divided by the total number of people in this leaf node, and the probability of no equals 125 divided by the total number of people in this node. And if we do the math, we get 0.336. Now that we have measured the Gini impurity for both leaf nodes, we can calculate the total Gini impurity for using chest pain to separate patients with and without heart disease. Because this leaf node represents 144 patients, and this leaf node represents 159 patients, the leaf nodes do not represent the same number of patients. Thus, the total Gini impurity for using chest pain to separate patients with and without heart disease is the weighted average of the leaf node impurities. So to calculate the weighted average, we take the total number of people in the left leaf node and divide it by the total number of people in both leaf nodes. We then multiply that fraction by the Gini impurity for the left leaf node. Then we take the total number of people in the right leaf node, divided by the total number of people in both leaf nodes, and then multiply that fraction by the Gini impurity for the right leaf node. After we do the math, we get 0.364. Thus, the total Gini impurity for chest pain equals 0.364. And since I'm such a nice guy, I'm going to cut to the chase and tell you that the Gini impurity for good blood circulation equals 0.360. And the Gini impurity for blocked arteries equals 0.381. Good blood circulation has the lowest impurity. It separates patients with and without heart disease the best. So we will use it at the root of the tree. Note, when we divided all of the patients using good blood circulation, we ended up with impure leaf nodes. That is to say, each leaf contained a mixture of patients with and without heart disease. That means the 164 patients with and without heart disease that ended up in this leaf node are now in this node in the tree. And the 133 patients with and without heart disease that ended up in this leaf node are now in this node in the tree. Now we need to figure out how well chest pain and blocked arteries separate these 164 patients, 37 with heart disease and 127 without heart disease. Just like we did before, we separate these patients based on chest pain and then calculate the Gini impurity value. In this case, it's 0.3. And then we do the exact same thing for blocked arteries. Since blocked arteries has the lowest Gini impurity, we will use it at this node to separate patients. Here's the tree that we worked out so far. We started at the top by separating patients with good circulation. Then we used blocked arteries to separate patients on the left side of the tree. All we have left is chest pain, so first we'll see how well it separates these 49 patients, 24 with heart disease and 25 without heart disease. Nice! Chest pain does a good job separating the patients. So these are the final leaf nodes on this branch of the tree. Now let's see what happens when we use chest pain to divide these 115 patients, 13 with heart disease and 102 without. Note, the vast majority of the patients in this node, 89%, don't have heart disease. Here's how chest pain divides these patients. Do these new leaves separate patients better than what we had before? Well, let's calculate the Gini impurity for it. In this case, it's 0.29. The Gini impurity for this node before using chest pain to separate patients is 0.2. The impurity is lower if we don't separate patients using chest pain. So we will make it a leaf node. Okay, at this point we've worked out the entire left side of the tree. Now we need to work out the right side of the tree. The good news is that we follow the exact same steps as we did on the left side. First, we calculate all the Gini impurity scores. Second, if the node itself has the lowest score, then there's no point in separating the patients anymore and it becomes a leaf node. Third, if separating the data results in an improvement, then pick the separation with the lowest impurity value. Hooray! We made a decision tree. So far, we've seen how to build a tree with yes/no questions at each step. But what if we have numeric data, like patient weight? Imagine if this were our data. How do we determine what's the best weight to use to divide the patients? Step 1. Sort the patients by weight, lowest to highest. Step 2. Calculate the average weight for all adjacent patients. Step 3. Calculate the impurity values for each average weight. For example, we can calculate the impurity value for weights less than 167.5. Dooba-dooba-dooba-dooba-dooba-dooba-doo, dooba-dooba-doo-boo-boo. Ultimately, we get 0.3 as the impurity value for this weight. And then we calculate the impurity values for the other weights as well. The lowest impurity occurs when we separate using weight less than 205. So this is the cutoff and the impurity value we will use when we compare weight to chest pain or blocked arteries. Now we've seen how to build a tree with yes/no questions at each step and numeric data like patient weight. Now let's talk about ranked data like rank my jokes on a scale of 1 to 4 and multiple choice data like which color do you like, red, blue, or green? Ranked data is similar to numeric data, except now we calculate impurity scores for all of the possible ranks. So if people could rank my jokes from 1 to 4, 4 being the funniest, we could calculate the following impurity scores. Joke rank less than or equal to 1, joke rank less than or equal to 2, and joke rank less than or equal to 3. Note, we don't have to calculate an impurity score for joke rank less than or equal to 4 because that would include everyone. When there are multiple choices, like color choice can be blue, green, or red, you calculate an impurity score for each one as well as each possible combination. For this example, with 3 colors, blue, green, and red, we get the following options. Color choice is blue, color choice is green, color choice is red, color choice is blue or green, color choice is blue or red, and lastly, color choice is green or red. Note, we don't have to calculate an impurity score for the color choice blue, green, or red since that includes everyone. Bam! Now we know how to make and use decision trees. Tune in next time for random forests. That's when the fun really begins. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more, please subscribe. And if you have any suggestions for future stat quests, well, put them in the comments below. Until next time, quest on!